Okay, so we are in the process of talking about context-free grammars. We started out talking about, I didn't start out, but we talked about simple grammars last time. So simple grammars had this form, a non-terminal followed by some number of terminals, with the additional restriction that any pair of non-terminal to terminal appeared at most once in the grammar. We talked about ambiguity. So we find that grammars, we redefined this, I think, to be that if there was some string in the language that you could construct multiple parse trees for, that said that that grammar was ambiguous. So to prove a grammar is ambiguous, just find some string, construct two different parse trees such that a depth first search through that parse tree generates that string, and you prove that the grammar is ambiguous, which is great. So here are a couple of examples of generating that. Two different parse trees for the same string, not good. We can, of course, rewrite grammars to remove that ambiguity. It's Friday for me too. I can't talk. So we're moving forward now to thinking about how can we use grammars for real constructs? Because context-free grammars are what are most frequently used to model programming language syntax. So if you want to write a compiler with the task of saying, one of the first questions that's useful is saying, is this program in this language? So we need some way to answer yes or no to that question. Part of that is every programming language allows us to express some kind of mathematical expression. So let's take a look at a grammar. Here we have a grammar where our non-terminals are E and I. And we get productions with regards to these expressions. Our terminals, A, B, C, let's just say there are three legal variable names. We could say that A, B, and C represent variables or constants. Then we want to be able to do plus, times, and parentheses. Subtraction and division could easily be added to this. But here are some productions. An expression can resolve to a constant or a variable. An expression can be rewritten as an expression plus an expression, or an expression times an expression, or parentheses around an expression. Do we see how using these productions we could produce arbitrarily complicated mathematical expressions using plus or times? Is there any ambiguity in this? First of all, what would ambiguity look like or mean in this case? Because we want to have some kind of precedence rule for this, right? Math expressions have precedence. We want to evaluate times before we evaluate plus, unless there are parentheses. If we took these productions as such, is there any precedence rule about plus and times? How would those be evaluated without parentheses? First of all, is it possible to produce an expression that has a plus and a times without parentheses? Try to draw that out. What sequence of productions could you apply, kind of starting with an E, that would create something where we would need to have some kind of precedence specified, or doesn't do what you think mathematical precedence should do? It's pretty straightforward. We just go from E to So we're gonna do this. Gonna resolve this. Let's say it's an A. Gonna resolve this. Something like this sequence of productions where we go and produce A plus B times C. We don't really know or have any way of knowing what the precedence for this is. We know that according to expressions, we should do the B times C before we do A plus that result. But that's not inherent in this grammar. This grammar does not force an order of operations. So we can produce something that has multiple ways to try to figure this out, to actually evaluate it. So while this allows the construction of expressions with these components, and we're restricting variables to A, B, and C for simplicity, order of operations for expressions doesn't really exist. That's really difficult. So the question that I have for you is, what would it look like to try to put an order of operations into this grammar? How could you change this grammar to try to force multiplication happening before addition unless the addition is surrounded by parentheses? What would that look like? Start kind of in the abstract. What needs to change to do that?
You can't add like an extra variable to the.
Oh, you totally can, but that's the right answer too. We need extra non-terminals in this grammar to be able to do that. We can't just have E and I and be done. We need to force some additional or include some additional non-terminals in here to route things differently through this so that we can't route addition and multiplication and parentheses all at the same time. That is an excellent point. So what would that look like? Spend a little bit of time and think about what path through these non-terminals would need to be in order to force an order of operations. Really good point. Anyone having any luck? Anyone have any kind of big picture ideas about how you might do that? A surprisingly difficult problem. So let's start talking about it. So first of all, the grammar is ambiguous. A plus B times C, multiple parse trees that could generate. So that's the first big issue with this grammar. Right? Two different parse trees that generate the same expression. Not good. So let's see what we can do about it. The reason that it's ambiguous is that we don't force evaluation order. And if we do that, we end up having precedence. There's only one way to produce a particular string. If there's only one way to produce a particular string, then that can help us to be able to resolve orders of operations. So the rules themselves exist outside of the scope of the grammar, but we can also rewrite the grammar to have the precedence rules, which is necessary because you don't want to write additional rules for parsing strings that the grammar generates. So the answer to this question that I've posed you is challenging. I had no expectation that people would come up with an answer, but I think that by thinking it through and working through your own thought process for this, you can start to see how close was I? Was I on the right track? What was missing from my thought process? Because this can help train you to start thinking in a way that a compiler does. So here is an example of a grammar with precedence rules. First of all, take a few seconds and actually look at this grammar. Try to understand exactly what it is doing. Once you figure out or get a sense of exactly what it's doing or why it's working, see if you can draw out a parse tree for A plus B times C. Are there multiple ways to do that now? So we're working on a grammar to encapsulate precedence rules in mathematical expressions. So I just introduced this concept of a grammar for plus and times and parentheses, as well as a limited subset of variables or constants, A, B, and C. We found that this was ambiguous because there are multiple different parse trees that can generate the expression A plus B times C. So we're trying to remove the ambiguity from the grammar and encapsulate precedence rules into the grammar. Because A plus B times C is ambiguous in how you're going to evaluate it. With taking into account precedence rules, you want to do the multiplication before the addition. One could argue that you don't need to put that into your grammar, but then you need some additional program to go over a string that the grammar produces and apply the precedence rules to that string. We can argue that if we remove the ambiguity from the grammar, that there becomes only one way to evaluate a particular string that is generated from it if we look at the parse tree for how it is generated. For instance, you can imagine going back here and saying, do we do the plus before the times, or do we do the times before the plus? If we were to do some kind of bottom-up evaluation where we're going to say, what does this E represent? Well, it breaks down into a plus. So we're going to evaluate this at this level so that we know what this E is, so that we can evaluate this times. You see how we need to evaluate this plus before we evaluate this times, according to this parse tree. To know what this E even is to do this multiplication, we need to have evaluated this plus. But in this parse tree, we need to evaluate this times at this level before we can evaluate this plus. So depending on how the parse tree is built, we have different precedents embedded inside of the parse tree that's generated. So using this grammar instead, I will argue that that same kind of bottom-up logic of trying to figure out if there's only one possible parse tree, then there's only one way to evaluate that expression. And we'll see that this will force the evaluation order that we want when we construct the parse tree for an expression. So spend a little bit of time trying to analyze and understand this grammar, and then draw out a parse tree for A plus B times C, and see if that bottom-up evaluation matches the appropriate order of operations. I also want to point out one other aspect of this that I forgot to mention and is important because it ties back to something we were talking about the other day. When I talked about how grammar ambiguity can lead to evaluating certain instructions differently, this is one of those examples. I just want to tie this back to that idea where we have an ambiguous grammar. Now we're trying to represent mathematical expressions. And if we have that ambiguous grammar, now A plus B times C can be evaluated in two different ways. If we wrote a compiler that forced the left side evaluation and one that forced the right side evaluation, we could type something that the compiler would decide means what one compiler would say that the result of this expression is one thing, and another compiler would say the result of this expression is another thing. And there's a right answer when it comes to mathematical precedence, but you can imagine a grammar that is not based on math where that wouldn't be the case. We would just have two different ways to evaluate this instruction. So this is why having grammars that don't have ambiguity is very important, because then there is only one way to evaluate some instruction. It means this and only this. Find a parse tree. I think you all are in the process of generating this. I see this in one person's. But this is basically the only parse tree that you can generate to get A plus B times C. And if we do that bottom-up evaluation, you will see that we need to evaluate the multiplication before we evaluate the addition. There is no other way to evaluate this. With the E plus T, we need to know what this T is before we can do this addition. So to do that, we need to do this multiplication first. Take a minute to convince yourself of that. That in order to do the plus before the times, we need some way of utilizing this rule. We would need to surround this plus with parentheses. So this E is going to become a T, which becomes an F, which becomes the E under parentheses, which can then evaluate a plus outside of the times. So you'd end up with you start with the T times F. The T becomes an F, which becomes an E under parentheses. That's the route you have to take to be able to evaluate that plus before you evaluate the times. And we see that in order to get the plus, that becomes the first thing that you can do, which means that deeper in the tree, deeper in the logic, that's where the higher precedence things are. The lower precedence things are closer to the start of the grammar, and the higher precedence things are deeper down into the grammar, because we're going to be doing this deep tree where the bottommost things happen first. So this precedence means that you want to add a layer or a step for each possible order of operations, where the deeper ones are the higher precedence and the shallower ones are the lower precedence. And that way, when you construct this tree, the deeper ones are going to be the higher precedence, and the shallower ones are going to be the lower precedence ones. And the deepest order of operation in here is this parentheses. Because you have to get all the way to an F to be able to do it. So the E, T, and F stand for expression, term, and factor, which are mathematical terms for exactly this. So do note that it's really difficult to show that a grammar is ambiguous. You need to use a lot of intuition to find here is some string where I think I could generate two parse trees. Then you actually have to go through and write those two parse trees. So it's really tough looking at this grammar to say, is there such an expression where we can use to prove that this grammar is ambiguous? We can actually show that no algorithm exists that can always do this. That can always show whether a grammar is ambiguous. To be able to prove it in the brute force, we'd have to go through every possible string and show that none of those strings have two possible parse trees. And unfortunately, these languages are infinite, so we cannot iterate through all of the possible strings. There will always be a string that, regardless of the algorithm that we write, that the algorithm hasn't gotten to yet. Given an arbitrary end time to the algorithm, we'll always have more strings to parse. We can't say that the grammar isn't ambiguous unless we can show in general no such string can exist. Questions on grammar ambiguity? Being able to look at and read parse trees, grammars, constructing parse trees from grammars, and the at least concept of ambiguity in a grammar. It's kind of an abstract concept, but it's a very important one when you come down to writing your own programming language or writing a compiler for an existing programming language. You need to be able to write a grammar for it, be able to show that that grammar is not ambiguous for important mathematical ideas and even programmatic structures that have an order of operations to them. Unfortunately, there are some languages out there where there is just ambiguity in the language. And no unambiguous grammar can exist for this ambiguous language. An example of one such language is this language. A to the n, b to the n, c to the m, union a to the n, b to the m, c to the m. Take a second and figure out, think about, one, what does this language mean in English? Let's start there. Just that one question.
N A's followed by N or N B's followed by N C's.
Yeah, so we know there are a different number of A's and C's, but the B's can either be equal to the A's that come before it or the C's that come after it. Does that make sense? Second question, is the language context free? Can you write a grammar that represents this language? If you think it is possible, write it out. If you think it is impossible, prepare some kind of justification, just a logical justification, not a mathematical proof, for why you think this is impossible. I see that people are in the process of trying to write one. I just want to query people and say, who thinks this language is context-free? Who thinks that regardless of how far into this that you are, that a grammar exists, a context-free grammar exists for this language? One person says yes. Who thinks the answer is no? This language is not context-free and a grammar does not exist for it.
I don't wanna say that.
I love it. So we have one person for, one person against. And I guess potentially one or two abstentions. I don't know, Logan, do you have an idea? Earl, what are your thoughts? Not sure? All right, so we have one vote for context-free, one vote for not context-free, and another vote for not context-free. So 1 versus 2. So I'm gonna break this down into two components, the left side of the union and the right side of the union. So if this is not context-free, either the left side must be not context-free, the right side must be not context-free, or they both must be not context-free. So let's take a look at the left side of the union. We could write the following grammar to represent the left side of the union. We're gonna say that we have some starting non-terminal that says we need something followed by a C, or something that creates an A and a B, or nothing. So this allows us to have some number of C's. We make all of the C's, and then we transition into making all of the B's, all of the A's and B's together. So this forces A's and B's to do this. Come in together. Note that there's nothing in this language that specifies that N is different from M. The right side of the union. Oh no, did I do this wrong? Must have done this wrong. Where did this come in? There it is. Oops, I threw the picture all the way at the end of the animation, but here's the right side of the union. We generate an A beforehand, and then we eventually transition after making a bunch of A's into producing the B's and C's together, or terminating the grammar, terminating the string creation. So if you have a left side of the union and a right side of the union grammar, then you can make a new production at the beginning that says, now we're going to go down one path or the other path to generate that string. Because a string that is in this language either has to come from the left-hand side or the right-hand side. So we make an additional production that makes us choose from the beginning. Are we on the left side of the union or the right side of the union? So this is context-free, and this is one such grammar that would represent it. So do note that this creates kind of an ambiguity, right? We have no way of knowing before going in whether it's the left side or the right side. So when N is equal to M, we could generate from the left side or the right side. There's no correct answer to pick, which means there's no way to resolve this. We would need to force N equals M to come from the left side or the right side. And there's no way, if we force it to come from one side, that we could create a grammar for the other part without it. We need both parts to include the case for N equals M. Questions on that concept? Or anything about this ambiguous language, creating a grammar for this? I wanted to use this example because it's really good to show that languages that have a union, this gives you an additional tool. You can now break down and try to create grammars for the left side and the right side of that union separately, and then bring them together with a production like the S arrow, S1 or S2. Okay, let's kind of tie all of this together. We've done a lot of really abstract thinking, creating grammars. We're going to tie it all together. So we want to define a programming language precisely. We want to apply this to what we know. Of course, we can define programming languages with grammars. We talked about this at the beginning of the course. Usually, programming languages are specified using a grammar form that is called BNF. Backus Nor form. We're going to go into exactly what this means as well. So the grammar specifying addition and multiplication, if we wanted to rewrite this in BNF, would look something like this. So describing what these mean, plus and times are our terminals. Non-terminals are surrounded by brackets, and this colon equals means to be defined as, which is going to replace what we've been using as the arrow. So an expression is defined to be term or expression plus term. Term is defined to be factor or term times factor. So now instead of just having capital letters representing our non-terminals, if we use English words for this, it makes the purpose of the production clearer. So just like using solid, good variable names in a program, as soon as these non-terminals have meaning, then using words rather than symbols for that help to make that clearer. So terminals and non-terminals in the following production. Ready? Here it is. What are the terminals? What are the non-terminals?
While the only terminal.
Yeah. While is the only terminal here. A while statement is a non-terminal, an expression is a non-terminal, and a statement is a non-terminal. But the actual word, the keyword while, is a terminal. Does that make sense when we write a programming language? While just tells us that what is to follow must be some expression. While this expression is true, then execute this statement. There's a logical meaning behind incorporating the word while. You can't just throw it anywhere. You can't name a variable while. So this is why such keywords exist in all of our languages. They tell the compiler, which is just a program that is trying to interpret and determine whether this is a legal program in this language. When we use the word while, it tells us that what follows that must be this form that we are going to say has a particular meaning. Repeat statement while expression is true. So this just looks like a simple grammar production, but this is exactly what keywords do in programming languages. They are terminals in a grammar to be able to map to a grammar production like this. In addition, they help provide visual structure. So if you're reading a programming language, the while tells you what's happening, as well as makes it easier. And they make the compilers work easier as well. However, we don't have simple grammar productions in things like the expression rules on the last slide. What we want to move forward from this idea thinking is, what rules can we permit in our grammars that we can still parse efficiently? Because we want to be able to take any particular statement that is written by an end user, and we want to be able to parse it. We want to figure out, what does this mean in this language? We need to be able to do that efficiently. We don't want a compiler to sit there and take forever to be able to convert a programming language program into machine instructions. That should not take long. We will be coming back to this as we start talking about compilers the last couple of weeks of the course. There are two types of grammars, LL grammars and LR grammars, that will help us to be able to answer this question. What rules exist? How can we parse those rules efficiently? How can we write a grammar that is meant to be parsed efficiently? We're going to be coming back to this idea and expanding on everything that we've just talked about as a large-scale deep dive application eventually. But we want a little bit more background before we go into something significantly more complicated than what we're talking about, because I think being able to tie it to everything that we've seen throughout the course is important and useful. Questions on any of these ideas? Broad scope topics? Last thing we want to talk about, in general, what aspects of a programming language can be modeled by a context-free grammar? Any idea of what that restriction is? What are the limitations of what a context-free grammar can represent in a programming language? Because we're kind of running out of time, I'm going to do this one fairly quickly, but the answer to this is, it can model all syntax. But what is something that a context-free could not model? How about something like this? Char C equals 3.2. First of all, one, is this syntactically correct? It is. This is a syntactically correct statement. We have a rule. We cannot assign a character variable a real value. That is a semantic rule. What we have here is a legal expression. You have a variable type, a variable name, an equals, and a value. That's what we care about syntactically. That is a syntax that works. However, the meaning behind this is, I don't know what this means. Whenever you have a question like that, it's a semantic issue, not a syntax issue. So context-free grammars can't express things like typing.
So wouldn't your compiler technically say that's a syntax error?
It would not. Every one of these has a value, and it would say something else.
Or under the red squiggly?
It would definitely get a red squiggly, for
Yeah.
sure.
But
The red squiggly would mean a semantic error and not a syntax error. A syntax error is when you use, like, you're missing the R, CHA.
right.
That's not a variable type that it recognizes. So there's no, every one of these has a meaning in the language. It's just that you can't do, this does not map to a valid instruction in this language. We can't do something with this. It's like creating an English sentence. Dog jumps, swims, boy. Over lake. Into dog. Valid English sentence construction. It had a subject. It had kind of sort of a predicate, but there's eventually the rules kind of break down. It says this valid sentence has no real meaning. Like you can't map it to a sentence that has meaning. So that's what's happening here. Semantics is way harder than syntax, and syntax is hard by itself. But to be able to solve the semantics problem, we don't have anything as simple as the concept of a context-free grammar. So several methods for looking at semantics, nothing universally accepted. And this is an ongoing discussion among computer scientists. How should we map semantics? Is there a correct way to do this? Lots of different languages do this in different ways, and trying to figure out, is there a correct way? Are there ways that are better than other ways? That's ongoing discourse. So we're going to focus much more on the syntax problem than on the semantics problem, but be able to differentiate between a syntax error and a semantics error in terms of one, a context-free grammar can help solve, one, it cannot. So that's where we'll stop for the day. We'll come back to this next week. Well, not back to this. We will start the next topic. We have a very brief topic on simplifying context-free grammars. And then we will dive into some more of what we can do. We've talked about grammars. How do we model this with an automata? We're going to come up with an automata structure like a DFA or an NFA to be able to model context-free languages like the grammars that we've been writing. So that's coming next week. Have a good weekend. I will be in my office for the next hour if anyone has any questions about homework or any other issues with the class.
That's next Friday.
I think it's the week after next Friday. Yeah, so you'll get a study guide next Friday for an exam the week after. Thank you. Thank you.